If you want, you can maximize. Okay, that's perfect.
Perfect. Okay, so I will try to show the similarities between what I'm going to say and the previous presentation. And indeed, both presentations start from Wheeler graph. I guess that Travis already gave a good idea of why Wheeler graph were introduced and how they are connected with the Barrows-Wheeler transform. So what I'm going to show now is how it is possible to actually generalize the mechanism of Wheeler graph. Okay, I will just recall a little bit the definition of Wheeler graph. We have just seen it, but so I hope that at least at the end of the day, the definition of Wheeler graph should be okay after these two presentations. So intuitively, consider a graph or an automaton. Basically, it's the same structure. This is just a technical difference we make in the paper this presentation is based on. And so we say that this automaton is Wheeler if we can define a total order on the set of nodes having the following properties. The start node of the automaton must come first. Second, as you can see in this example, all nodes labeled A come before all nodes. So this node is only reached by some edges labeled A. This node is only reached by some edges labeled A. This node is only reached by some edges labeled A. Here B, B, C, and C. So I should respect the order of the letters, the alphabetical order. And the last property that I require is that if I consider any two pairs of two edges with the same label, then the mutual order of the start states should propagate the mutual order of end states. So for example, if I pick this edge and this edge here, then I have that 2 is smaller than 6, and consistently I have that 7 is smaller than 8. There is also this other example here with letter A. I use this example just to show that the definition is also consistent with a situation where I actually reach the same state. So in general, I just require that if this is smaller than this, that this state should be smaller than or maybe equal to this one. So this situation is consistent with the definition of Wheeler graph. And the reason why Wheeler graph are useful, I think was already given by Travis. And the reason is that I managed to, if I want to read patterns on the graph on the automaton, then what I obtain every single time, for example, if I start from the start edge, from the start state, and I try to read some considered string, for example, A, B, C, C, B, A, then I should end up in a set of consecutive states. And the reason why this actually works is that if I consider all strings recognized by state I, that is all strings that I can read, for example, starting from the initial state and ending in state I. So, for example, in the case of state 3, these strings are A and AA. Or, for example, in the case of string of state 5, these strings are B, A, B, A, A, B, and so on. Then these sets, respect the total order on the states of node from a lexicographically point of view. So this should be a bit more clear if I show this slide. The point here is that here I'm just repeating what I'm just explicitly writing what I just said. So for example, I3 is AA, A, and so on. And you can see that if I consider the colexicographic order, that is the order that compare two strings starting from the last character and proceeding backward, then this string is smaller than this string. This string is smaller than this string. This string is smaller than this string. This string is smaller than this string, and so on. So except for intersection, then every string here is smaller than every string here is smaller than every string here, and so on. This works this is a consequence of the definition of Wheeler graph. But now let's try to change perspective compared to the previous presentation. So in the previous presentation, we started from the Barrows-Wheeler's algorithm, and we said that Wheeler graphs are a good way to capture how the Barrows-Wheeler transform works. So now let's change perspective and let's start from Wheeler graph. So now it is possible to interpret every single graph as a Wheeler graph, as a Wheeler automaton. Unfortunately, if I just keep to the standard definition of Wheeler automata that I've just given, this is impossible, because if I consider the language interpretation of Wheeler graph, that is the expressive power, then I can see that if an automaton is Wheeler, then by using only Wheeler automaton, I'm able to capture only a very small subclass of regular languages. So, for example, if I consider unary languages, I mean languages whose alphabet consists of just one letter, then it is easy to see that such a language is Wheeler if and only if it is either finite or co-finite. So the idea of the paper that I'm presenting is to try to maintain the structure, the idea of Wheeler graph, but somehow changing in such a way that it can be applied to generic graphs. So, okay, I like the fact that I can rely on intervals, that I have this easy way to follow strings, as for example Wheeler explained in the previous presentation. I can very easily keep track of patterns that I read on the automata. But since this is impossible for generic graph, is there a way to adapt this mechanism in such a way that it can be applied even in more general situations? And the answer is positive, is yes. And the intuition is the following. In a Wheeler graph, what I require is a total order on the set of states. And this is just the formal way of writing the example that I presented earlier. That is, if I consider a state reached by edges labeled A, they should come before states reached by edges labeled B, which should come before states reached by edges labeled C, and so on. And here, axiom 2 is simply the comparison property between two edges with the same label. So the intuition is that we can drop the assumption that the order is total, and we can be fine with just the requirement that the order is partial. We don't need to change axiom 1, and we slightly need to change axiom 2. If you recall the example, in axiom 2, I was requiring that the mutual order of starting states should propagate to the mutual order of end states. Here, I'm just requiring the opposite. That is, the mutual order of end states should propagate to the mutual order of start states. In the setting of Wheeler graph, this is 100% equivalent to the old definition, because I'm just picking the contrapositive statement. But remember that now we are just considering partial order. So these two statements are not logically equivalent any longer. So this is the definition that we introduced in our paper. And the reason why we needed to change axiom 2 is that as I try to show, the enjoyable properties of Wheeler graph strongly rely on colexicographic order on strings, and colexicographic order on strings works backward. So I start from the end of the string, and if the last two characters are equal, then I proceed backward. If they're equal, then I still proceed backward, and so on. So the idea is that in order for this to work, I need some backward compatibility, not a forward compatibility. I guess the reason why, I may ask Travis, I don't know, the reason why in the original paper Axiom 2 was defined the other way, that is in such a way that a forward compatibility was guaranteed, is that this forward process is the process that is needed to find a pattern on the graph. But from a logical and from a structural point of view, here what we need is a backward compatibility in order for things to work fine. And the reason why this definition is more general than the previous one is that now it can be shown that every single automaton admits some ordering with these properties. And the intuition is that, as one may expect, the reason why this always works is that now the order does not be total, it can also be partial. So letting the order be partial is basically what was saying Travis before. If the order is partial, I'm allowing some edges to cross. Okay, I say I don't care about some edges crossing. But from an algorithmic, from a computational point of view, we will see that the more the order is close to be total, the better. So just a very quick example. Consider the automaton in the figure. It can be easily shown that using some well-known properties of Wheeler graph that this graph cannot be given a Wheeler ordering. Basically, the reason is that here there is this cycle. But we can, for example, define a partial order which satisfies the properties that I've just presented. Such a partial order, for example, may be the one given by the Hasse diagram on the right. This can be easily checked. Now the point is, if I, in general, consider a partial order, then I can divide all the elements of the partial order into a number of totally ordered subsets. This works for every single partial order. In the worst case, I just pick singletons, but for example, in the case of this partial order, I can pick 0, 1, 3, 6, and 4 to 5, because this means from this diagram it follows that every two pair of elements here are comparable and every two pair of elements here are comparable. This is just very general. And there is a well-known theorem, Dilworth theorem, stating that the cardinality of a minimum size partition into totally ordered sets is equal to the cardinality of a largest anti-chain in the partial order. An anti-chain is simply a subset of elements such that every two elements in the subset are not comparable. So, for example, here the subset consisting of 3 and 4 is an anti-chain because 3 and 4 are not comparable. And since we have explicitly shown a partition into two elements by Dilworth theorem, it follows that, for example, it can exist an anti-chain of cardinality 3. That is, if I pick any three elements here, then at least two of them must be comparable. So it makes sense to measure the complexity of a graph of an automaton by considering the smallest p, the smallest cardinality of a partition into totally ordered sets. The point here is that in general a graph may admit several such orders. So in order to obtain a measure that only depends on the structural complexity of the graph, I should consider all possible lexicographic order on the graph and then picking the smallest such cardinality of a chain partition. So now it makes sense to say that this P somehow says how much a graph is difficult, is complex. And from the previous discussion, it follows that a graph is Wheeler if and only if this quantity P is equal to 1, because a graph is Wheeler if and only if the order is total, and trivially a total order admits a partition into just one totally ordered set. So in general, all results so all, as I was saying earlier, all algorithmic results depends on this quantity P, and as one may expect, the lower P, the better. This is an explicit definition of a colexicographic order which works for every single graph automaton. So now every automaton is this quantity P that can be associated to the automaton. I will skip details. And as Travis was saying, the nice property of Wheeler automaton is that if we start from, if I want to read a string starting from the start state, then I always end up in a set of consecutive state. More generally, the property is the following. If I start, for example, from some consecutive states, 2, 3, 4, 5, and I read a letter, say C, when I say I read a letter, I just mean, okay, just pick every single state I start from, 2, 3, 4, 5, and consider all edges that I can follow by reading C. So from 2, I can go to 7. From T, I can go nowhere by reading C. From 4, I can go nowhere. And from 5, I can go to 7. So to sum up, I end up in this set of states. And once again, I get an interval. So this means that by induction, in general, if I start from an interval and I read a letter, then I end up in an interval. Then if I read once again another letter, I still end up in an interval, and so on. So if I read a string in general, then if I start from an interval, I end up in an interval. And now the only difference for generic graph is that in the worst case, I need not keep track of just one interval, but I need P intervals. And now I don't have time to show details, but what can be shown is that actually all compression and indexing properties of Wheeler graphs still work. In other words, it is easy to generalize a compression representation of Wheeler graph to colexicographic automaton. So this kind of graph can be compactly stored. This means that the complexity of the storing mechanism basically depends on this quantity P. And in order to keep track, in order to read a string, as I just said, I need to keep track of P intervals. And this can be done by the same mechanism or the forward algorithm that is used, for example, in FM index. This is just a generalization where I don't need just one array. In the standard forward algorithm, I need a number array. Now you just have to think that you need the whole number of arrays multiplied by P, because I kind of need an array for every interval, but the general idea is the same. Okay, I'm not going to present this. This is just a way of comparing Wheeler automata and arbitrary automata. And I just mentioned that there are also some consequences, some more theoretical consequences about Wheeler automaton, because they somehow describe how much an automaton is non-deterministic. But okay, this is just a very interesting theoretical result, but probably it's not directly connected with what I just explained. Okay, I guess this is what I meant to present, at least to give a glimpse of the computational and algorithmical application of colexicographic automata. Yeah.
Thank you very much. But you have 1 more minute, so if you want to show the slide of the further directions, that might be interesting.
Okay.
We're not late, so that's not a problem.
Right, I don't know why. Okay. Yes, in general, when I turn a non-deterministic finite automaton into a deterministic finite automaton by the standard power set construction, what happens is that I obtain a blow up in the number of states. That is, if I start from an n states, then the number of states that I obtain is exponential in the number of states of the non-deterministic finite automaton I started from. So what we actually showed is that it's true that in worst case we obtain an exponential number of states, but this number is not exponential in the number of states, but it's exponential in this quantity p. So this means that it was already known that Wheeler automata are very special because they are a class of automata such that if I transform a non-deterministic finite automaton into an equivalent deterministic finite automaton, then I don't have this exponential blow up. I just have a linear number of states. But even in general case, this blow up must be exponential, but the quantity that makes it exponential is p, is not n. So this means that all problems that are difficult on non-deterministic finite automaton can be turned into easy problems on deterministic finite automaton by applying algorithm, by simply transforming the non-deterministic finite automaton into a deterministic one, and then I obtain algorithms that are fixed parameter tractable with respect to this quantity p. So this just shows once again that this quantity p seems to nicely describe the complexity of the graph.
Okay, thanks again. Are there any questions? Let's wait a little bit if somebody has some question. So it looks like there are no questions. So thanks again for your nice talk. And I'm inviting to the stage the next speaker, who is Garance Godel. Hi, Garance. Garance is going to give the talk. One moment. So if Nicola can get back, because we have the first question. Okay, Nicola, so have you tried computing p for some regular expression?
Yes, indeed. It was one of the things that we planned to do. For example, it's possible to show quite easily that the quantity p can be nicely. I mean, there is a very easy dependence between a language I start from and some Boolean operation that I make on the consider or the considered languages. So, for example, if I start from a language whose p is equal to p1, I pick another language whose p is equal to p2, and for example, I take the union. Then, in the worst case, the resulting p is equal to p1 plus p2. So this somehow suggests that I can describe the complexity, the hierarchy of regular languages seen as regular expression by p. Yes, let's say that we are trying to work on this, but it's still on progress. Still, it seems to work quite nicely, yes.
Okay. Thanks again. Thanks.